In this video, we're going to look at the area between two curves. So for example, we might have two curves that look like this and be wanting to find the area between them over a certain section of the x-axis. So for example, we might know these x values. We'll usually call them x equal a and x equal b. And we usually have the formula for the two curves. So we'll often call the curve on the bottom, call it y bottom, or sometimes yb for short. And then the curve on the top, we can call it y top, or sometimes just yt for short. So area between those two curves along a certain section of the x-axis. That's what we're going to be talking about. The way that we would start to find that area is to cover the area in vertical slices. So we'd be covering it in infinitely many, infinitely thin vertical slices like this. And if we just zoom in on one of these vertical slices, let's look at this picture over here. So here's a zoomed in version of one of these vertical slices. Let's think about its height. So a vertical slice would be running from y bottom up to y top. And so if we just subtract those two y values, you'd have yt minus yb would be the height of your slice. And then if you think about the width of your slice, well, we're just going a tiny little distance in the x direction, which we would call dx. So those are the dimensions of that vertical slice. And if we wanted to find the area of that vertical slice, then we would just multiply those dimensions together. So we'd say the area is yt minus yb times dx. So that's the area of just one of those vertical slices. And for short, we're going to call this dA. So dA just represents the area of a vertical slice. Okay, then to get the area that we're looking for, we're going to say area is the sum of infinitely many of these slices. Or if you phrase that in terms of integrals, you would say area is the integral of dA, because what the integral is really a sum of infinitely many, infinitely tiny things. And then that leads us to the formula that we're going to be using today. So area would be the integral over the appropriate x values, so integral from a to b, of what are we integrating? Well, just the area of one of those little vertical slices. So y top minus y bottom, all times dx. So I'm going to put a star beside this, and we're going to do a few examples, probably 3 examples, to practice this formula. Our first problem is to find the first quadrant area bounded by y equals 16 minus 4x squared. Well, sketching a curve is going to be quite important in these problems. So let's sketch maybe from x equals 0 to say x equals 4, just get a sense of what's going on. So at x equals 0, our curve is up here at 16. At x equal 1, our curve is looking like, our y value is looking like 12. So I'll just say 12 is here. And then by x equal 2, oh, we're down at 0. Okay, so our parabola is doing something like this. And we're saying find the first quadrant area. So we only want the portion of the area where x and y are both positive. In other words, we're not interested in this left side of the parabola. We're only interested in the right side. Okay, so I think I'll label things. So that's what's going to be acting as our y top. Our y bottom is just formed by the x-axis. And if we think about the equation of the x-axis, that's y equals 0. Okay, and then we need to make sure we know which x values we're going to integrate over. So it'll be from x equals 0 to x equal 2. So I think we're all set to do our area calculation then. The general formula says area is going to be the integral from a to b, and what you're integrating is just the area of a vertical slice. So it looks like y top minus y bottom times dx. Great, so let's plug in. We're going to integrate through x values 0 to 2. Y top is 16 minus 4x squared, and y bottom is 0. So our integrand will just look like that, and then we've got our dx on there. So at this point, you could do a little bit of simplification, because our integrand would really just become 16 minus 4x squared. And that way we could go ahead with our integration. So now integrating, we'd have 16x minus 4x cubed over 3. And we're going to evaluate that at 2 and then at 0. So plugging in 2, we'd have 32 minus 32 over 3. And then we need to subtract off the value when we plug in x equals 0, which is 0. Okay, so if we put everything over 3, we would have 64 over 3 for the final value of our area. So next problem we're going to try, we'll find the area between y equal x squared and y equal x plus 2. Okay, well, one way to approach this would be to just make a sketch. So let's try that approach first. I'll go a couple of units either way in the x direction. And let's start to plot our parabola. So that'll pass through 0, 0. When x is either plus or minus 1, y is 1. And then when x is plus or minus 2, y is 4. So we get those points on our parabola, and our parabola is looking something like that. So there we go. Then our other curve here, the y equal x plus 2, that's a line. Might do that in a different color. So when x is negative 2, y is 0. And then as we move 1 unit in the x direction, y is just going to increase by 1. So it's doing this sort of thing, and that gives us our line. Okay, and then I usually get in the habit of just labeling the curves because we are going to need the formulas when we set up the integral. So we were able to figure out, just from making a clear sketch here, that the x values we'll be interested in will be from -1 to x equal 2. And then we're capturing the area between those two curves. We can also figure out that it's the line that's going to be the top curve in the parabola that's going to be the bottom curve. Now, let's say that you hadn't done your sketch that carefully, and let's say you wanted an algebra way of figuring out where the curves intersect. Okay, so if you want the intersection of any two curves, what you can do is you can set y equal to y. So that's going to force the curves to intersect. And then we're going to figure out the x value where that happens. So just plugging in the equations of those two curves, we'd have x squared equal x plus 2. Could move everything over to one side, and then we could factor. So that gives us x minus 2 times x plus 1 equals 0, and that's how we'd figure out our x values. So x values 2 and -1 are the two x values that we found in our sketch where those curves intersect. Okay, so now we've got an algebra and a geometry approach, but to figure out which curve is the top one and which curve is the bottom one, it's always best to do a sketch. So area is going to be the integral from a to b, and what we're integrating is the area of a vertical slice. So that would be y top minus y bottom times dx. Okay, in this particular situation, our x values are going from -1 to 2. We decided that y top, just from looking at our sketch, y top is the line, y equal x plus 2. So we're going to go x plus 2 minus y bottom is the parabola, y equal x squared. So we're subtracting off x squared and then multiplying by dx. And now we're good to go with the integration. So integrating, we get x squared over 2 plus 2x minus x cubed over 3, and we're going to evaluate this at 2 and then at -1. Okay, so plugging in 2, we'd have 2 squared over 2, which is 2, so it's looking like 2 plus 4 minus 8 over 3. And then we need to subtract off what we get when we sub in -1. Okay, so that's going to be 1/2 minus 2 and then plus 1/3. So you can do that on your calculator if you want. That comes out to 9/2. Now let's find the area bounded by a parabola, y equals 0, x equal 2, and x equal 3. So again, let's draw just at least a quick sketch. So this is the same parabola that we saw in one of our earlier problems here. Its x-intercept is going to be at x equal 2. Y-intercept at y equals 16. So our parabola is doing something like this. And then beyond x equal 2, it's just going down into negative y values. So by the time we get to x equal 3, the y value is going to be down at -20. And we're only going to be interested in just the right side of that parabola. All right, so the area that we're interested in, we want the area between the parabola and y equals 0. Well, remember y equals 0 is the x-axis. And between x values 2 and 3. Okay, so x value 2 is there, 3 is there. So in other words, we're talking about this area in here. So let's label things. The y top is going to be the x-axis, which is y equals 0. The y bottom is coming from our parabola, y equals 16 minus 4x squared. And the x values that we're interested in, 2 and 3. So we're going to say the area will be the integral from a to b of the area of a vertical slice, which looks like y top minus y bottom times dx. So going from x values 2 to 3, our y top is 0. And then subtracting off y bottom, okay, we need brackets here because y bottom has 2 terms in it. 16 minus 4x squared all has to get subtracted off. And then that's all multiplied by dx. So let's clean up our integrand. But our integrand, if we actually distribute that minus sign, it's minus 16 plus 4x squared that we want to integrate. All right, so let's integrate that. Negative 16x plus 4x cubed over 3. And we're going to evaluate at 3 and then at 2. So let's plug in here. Plug in 3, we're going to have minus 48 plus 36. And then we're going to subtract off the value at 2, which is going to be negative 32 plus 32 over 3. So final answer for the area comes out to 28 over 3. So we've now done 3 examples of finding area using vertical slices, and we're going to take a look at another method for finding the area between 2 curves. So sometimes it's inconvenient to take vertical slices, and I want to show you a picture of when that might happen. So imagine that you've got 2 curves forming the left and right boundary of our area, something like that. And then imagine that you've got horizontal lines forming the top and the bottom of the area. So the area that we're trying to calculate looks like that. Now let's think about why vertical slices would not work very well here. So imagine covering this area here with vertical slices. So one vertical slice might look like this, another one might look like that, another one might look like that. So if we ask what curve is forming y top, well, for the vertical slice on the left, it's this curve here. For the vertical slice in the middle, it's the horizontal line that's acting as y top. And then for the slice on the right, y top is this sort of curvy curve that we're seeing on the right side. So the problem with this setup is that y top is different for all of these slices. That's not good. So we don't have a consistent curve that is always forming y top. And the same thing goes wrong with y bottom. So sometimes y bottom might be the left curve or the horizontal line or the right curve. So if we summarize what's going wrong here, we would say y top varies and y bottom varies. So the solution is to not use vertical slices. We're going to instead use horizontal slices. So let's instead take horizontal slices. So it's the same picture as we had before. So on the left, we've got this curve. On the right, we've got that curve. And we're going to call these curves x left and x right, or sometimes we'll just write xl and xr for short. So the left boundary, x left, the right boundary, x right. Okay, and then we've got 2 horizontal lines that are forming the top and the bottom. And because those are horizontal lines, they just have equation y equals something. So we'll say the bottom one is y equals c, and the top one is, say, y equals d. So the idea is to fill this area with a whole bunch, in fact, infinitely many, of these infinitely thin horizontal slices. And let's just zoom in on one of these horizontal slices. So zooming in on it over here. Here's a zoomed in version. of this horizontal slice. So let's think about the length of it. Well, it would be running from x left to x right. So if we subtract those two, the length would be xr minus xl. And then the little bit of height would be just a tiny change in the y direction, so that would be dy. Okay, so let's think about what the area of one of these horizontal slices is. In symbols, we'll call the area of a slice dA. So we call it dA just because it's a tiny chunk of area. Remember that a differential represents a very small change in your variable. So it makes sense to call the area of a slice dA, tiny chunk of area. And what is that area specifically? Well, just looking at the dimensions of our slice, x right minus x left times dy. So that gives us that little formula there. Okay, so that's the area of a slice. And then if you want the area of your entire region, area is the integral of the area of a slice. So this is going to be our second key formula. I think I might write down the two key formulas side by side just so we can compare them. And then we're going to do some examples using these horizontal slices. Okay, so the two situations we've seen, we saw vertical slices first, and then we just most recently saw horizontal slices. In either case, what we're doing is we're calculating an area. So if we're doing vertical slices, they're going to say area is, well, it's going to be the integral of the area of a vertical slice, which is y top minus y bottom, times dx, and then it would be x values that you would want on your integral. We usually just call those x values a and b. If you're doing horizontal slices, then you're going to say, well, area is going to be the integral of, and then we need the area of a horizontal slice. So that would look like x right minus x left times dy. And because we're integrating with respect to y, we would want y values on the integral. And then just the generic name or the notation that we usually use for y values is c and d. Right, so let's practice using this formula here for horizontal slices. So let's find the area bounded by y equal x plus 1, x equals 0, y equal 2, and y equal 3. Well, I would definitely think about drawing a sketch here. So let's start by graphing the line y equal x plus 1. So I'll just make some room along our x-axis here. So when x equals negative 1, y is 0. And then as we take a step in the x direction, y is just going to increase by 1. So we're getting that sort of picture for our line. Okay, so we want the area bounded by that line that we've just drawn and x equals 0. Okay, remember x equals 0 is the y-axis. So every point along the y-axis has x coordinate 0. And then we're interested in a couple of different y values. So when you say y equal 2, that's a horizontal line. So y equal 2 is there, and y equal 3 is a different horizontal line. Okay, so now we can visualize the area that we're interested in. It's this area in here. So if we tried to approach this using vertical slices, it wouldn't work very well because some vertical slices, y bottom would be the horizontal line, but for other vertical slices, y bottom would be the line y equal x plus 1. And whenever you're getting that inconsistency where sometimes y bottom is one thing, sometimes y bottom is another thing, that would mean that you would have to break the problem up into a couple of different integrals, and that would not be a fun way to solve the problem. So instead, we're going to think about doing some horizontal slices, and let's see if that works better. So imagine laying out some horizontal slices through this region. See, that's going to work really nicely because for every horizontal slice, x left is going to be 0. And for every horizontal slice, x right is going to be coming from this equation, y equal x plus 1. So the only catch here is that we have to take this equation, y equal x plus 1, and we need to just solve it for x. So if we bring the 1 over to the other side, we'd have negative 1, or y minus 1 equals x. In other words, just solving for x right equals y minus 1. So since we're going to be integrating with respect to y, we need both x left and x right to be expressed in terms of y. In other words, solve for x in both equations. And that's what you're going to need to do the integration. Okay, so definitely horizontal slices are the way to go here. X left will be 0 for every horizontal slice, and x right will be y minus 1 for every horizontal slice. We also know what y values we're running through. It's just from 2 to 3 in the y direction. So we're ready to set up our integral. If you're using horizontal slices, then the area is going to be the integral of whatever the area of a horizontal slice is, which is x right minus x left times dy. And then because we're integrating with respect to y, it's y values that are going to go on the integral. So we're going to integrate from 2 to 3. We've said that x right, I think I'll just highlight the relevant stuff here. X right is y minus 1, x left is 0, and we've already used our y values there. Okay, so x right, y minus 1, subtracting off x left, which is 0, and integrating with respect to y. So because you're integrating with respect to y, you want everything in your integrand to be expressed in terms of y. That's why you can just call this x right. We wouldn't know how to integrate that. We have to actually say x right is y minus 1, and that way we can get the integration done. Okay, so this minus 0 here, not necessary from an algebra point of view. So we can go ahead and do our integration now. Y squared over 2 minus y, and we're going to evaluate at 3 and then at 2. So plugging in, we get 9/2 minus 3, and then we subtract off the value at 2, which happens to be 0. So final answer then for our area is 3/2. So let's try a couple more examples like that. And one of the things we're specifically going to focus on is this idea of taking an equation and then needing to solve it for x. So let's find the area bounded by the parabola, x equals 3, y equals -1, and y equals 2. Well, again, first step here would be to make a sketch so that we can get a sense of what's going on. So I'm going to start with plotting the parabola. So when x equals 0, y is -2. When x is plus or minus 1, y value is -1. And then by the time we get to x equals plus or minus 2, our y value is going to be 2. So this is just like our familiar y equals x squared parabola, but it's shifted down by 2 units. Okay, so there's our parabola there. Now what else do we have? We've got x equals 3. So remember, x equals something is always going to give you a vertical line. So we've got this vertical line, x equals 3. And then we've got a couple of different y values. Okay, something like y equals -1, that's a horizontal line. So here's one horizontal line, and then the other one's at y equals 2. Okay, so I'll just label these things. Y equals 2, y equals -1. And then we've got our parabola. I might label that down here, y equals x squared minus 2. And then we've got our vertical line, x equals 3. Okay, so the area that we're looking for is this area in here. That's the area bounded by those 4 curves. Usually our go-to is to think about vertical slices. Vertical slices are usually sort of intuitively easier because people like integrating with respect to x. So you could try throwing some vertical slices on here and you could see, oh yeah, that's not going to work well because sometimes y top will be the parabola and sometimes it'll be the horizontal line. So that's not good. Let's see if horizontal slices would work better. So let's imagine throwing a bunch of horizontal slices in here, just covering that area with horizontal slices. Hey, that's going to work well because every horizontal slice will have the parabola on the left and the vertical line on the right. So that's exactly what you want to see when you're setting up those slices, is you want the same curve acting as x left for all your different slices, and you want the same curve acting as x right for all your different slices. Okay, so let's see if we can say what x left and x right are. I'm going to do the right one first because that's easier. So x right is just 3. X left is going to be a little more algebra. So we're going to need to take the equation, the y equals x squared minus 2, and we're going to need to solve that for x. So we could say y plus 2 is equal to x squared. In other words, if you take square roots of both sides, you could say x is going to be either plus or minus the square root of y plus 2. Okay, now sort of strange that we're getting two possibilities here, but what this represents geometrically is just the two halves of the parabola. So the left half of the parabola has equation x equals minus root y plus 2. And then the right half of the parabola has the equation x equals root y plus 2. That's just because on the left side of the parabola, the x values are negative. So you get x equal negative root. And then on the right side of the parabola, the x values are positive. So you get x equal positive root. So you just need to look at the picture and figure out that, oh yeah, we're just interested in the right side of the parabola. So we're going to make the choice x equals positive root y plus 2. And that's going to be our x left. So I'll highlight the things we're going to need. We need our x left, we need x right, and we know which two y values we're going to be integrating between. So we are good to set up our area. So our area is going to be the integral of whatever the area of a horizontal slice is. So x right minus x left times dy. And then you just want to put your y values on that integral. So let's do the y values first. We're going to be going from -1 to 2. And then based on our discussion here in the boxes, we know what x right and x left are. So x right is 3, and we're subtracting off x left, which is the square root of y plus 2. That's going to get integrated with respect to y. Great, so we've set up our area. We don't need to look back at our diagram anymore. And now it's just a matter of doing our integration. But there's something particularly tricky going on in this problem, and that is that we're going to want to do a little substitution to get this integration done. So we'll get a little bit more practice with substitution along the way. So what's tricky here is that you've got this root y plus 2 as opposed to just a nice root y. So what we're going to do is we're going to sub u equal y plus 2, and that's going to make everything look a lot nicer. So if u is equal to y plus 2, then du is the same thing as dy. So that's good. And then you may remember that when you're dealing with definite integrals, you want to change your y values over into u values. So if y was equal to -1 and 2, let's figure out what that means for u. So just use the fact that u is equal to y plus 2 and sub in y equal -1. That means u equals 1. And if y equals 2, that means u equals 4. Okay, so that gives us everything that we need to rewrite our integral. So I would just put that substitution discussion in a box, and then we can just follow from our previous step and say the integral that we had is equal to this new integral. So our new values for u become 1 and 4, and our integrand becomes 3 minus root u. dy is the same thing as du. So we're able to rewrite that integral. That's now nice and friendly, and we can get that integration done. Okay, so just continuing on a new page here, we've got this integral from 1 to 4 of 3 minus root u, integrating with respect to u. So let's do our integration. We'd have 3u. This root u, you can think of that as u to the 1/2 if that makes it easier for you to do your integration. So when you integrate, it's going to be u to the 3/2 times 2/3. And then we'll just evaluate at our u values, which are 4 and 1. So subbing in 4, you'd have 12 minus 2/3 times 4 to the 3/2. Okay, well, 4 to the 3/2 is equal to 8. So this part here just comes out to minus 16 over 3. And then we're going to subtract off the value at 1. So that's 3 minus 2/3. So final answer, 13 over 3 for our area. So that was another bit of practice with finding the area using horizontal slices, and we also did a substitution along the way. So that was a multi-concept problem. So in this example, we're going to look at the area bounded by y equal x squared and y equal 2x. And we're going to do two parts. We're going to do one using vertical slices and then the other one using horizontal slices, just to make sure we're really clear on those two different methods. Notice that it says set up the area. So what that means is that we just want to write down the integral that calculates the area. We don't actually need to do the integral calculation itself. So for both parts, we're going to need a sketch that we can refer to. So let's make a quick sketch of our parabola. So there's our parabola there, and then we've got the line y equal 2x, which passes through 0, 0, passes through 1, 2, and passes through 2, 4. Okay, so our line's doing that. And so the area that we're looking for is just the area between those two curves there. So let's say we wanted to approach this using vertical slices. Okay, so if you want, you can just draw one vertical slice in there to remind yourself what you're doing. So you'd need to know what y bottom is. It would be coming from the parabola, so it would be x squared. And then you want to know what y top is. And that's coming from the line, so that would be 2x. And then you're going to want to know your x values, which are ranging between 0 and 2. Right, so I'll just highlight. So area is going to be the integral of whatever the area of a vertical slice is. So y top minus y bottom times dx. And then in order for the integral to be set up, you want to actually plug in what is y top, what is y bottom. So we'd go 2x minus x squared times dx, and then just make sure that we've got the correct x values on there. So integral from 0 to 2. So this is what's considered to be set up. Okay, let's try the same thing using horizontal slices. So this will be part B. So I'm going to redraw our picture. Remember, we had the parabola, and then we had the line y equal 2x. And this time we're going to fill in this area using horizontal slices. So first thing you might think about is just what y values would I be ranging between? So be y equal 4 and y equals 0. That would be interesting to us. This point up here is the point 24. Okay, so we've got y values figured out, and then we need to do x right and x left. Okay, then we need to do the same thing for the right boundary. I'm going to do that calculation over here. So that's coming from the parabola y equal x squared. All right, now we want to solve this for x. So it might look better if we write this the other way around, x squared equal y. We can take square roots, but remember that there will be a plus or minus option. So x can be either plus or minus root y, and we need to decide which one it is. So I'm just going to draw a picture down below here. So let's think about the two halves of the parabola. There's the left half of the parabola here, and then there's the right half of the parabola there. So the left half of the parabola has equation x equal negative root y. The left half is where the x values are negative. And the right half has equation x equal positive root y. So you just want to look at your picture and figure out, oh, am I using the left or right side of the parabola? Well, it's the right side of the parabola that we're using. So we want to use x equal root y. And that's what's forming the right boundary. So we're going to call that x right. So the correct equation for that red line that we're seeing in our picture, that's y equal 2x. So let's solve for x by dividing both sides by 2. And then we can just solve for x by writing x equal y over 2. That's going to be our x left. And with that, we've got the correct x left, we've got our x right, and we've got both of our y values. So I think we're good to go in terms of setting up our integral. So for horizontal slices, you want to say area is the integral of whatever the area of your horizontal slice is, x right minus x left times dy. And then because you're integrating with respect to y, you would want y values on that integral. So our y values are going from 0 to 4. X right is root y. And then we're going to subtract off x left, which we figured out is y over 2. Just put brackets around your integrand, and then times dy. And that's our integral all set up. Remember, the point here is not to evaluate the integrals, but just to make sure we're comfortable with both the vertical slice and the horizontal slice process. Last problem for this video, let's find the total area bounded by the parabola, the square root function, x equals 0 and x equal 2. So let's draw a picture. We know we're going to be interested in x values between 0 and 2, so we'll put those on there. We'll graph our parabola, so passing through 0, 0, 1, 1, and 2, 4. Okay, there's our parabola. And then our square root function, let's do that in a different color, passes through 0, 0, 1, 1. And just to have a bit of sense of scale on the square root function, another point that's nice to plot is when x is 4, y is 2. Okay, so we're plotting y equal root x here, and that's got this sort of shape. Now we're interested in the x values between 0 and 2, and remember that x equal 2 is a vertical line. So we're getting a vertical line that looks like that. X equals 0 is the y-axis, just like that. And we're trying to find the total area between the parabola, the square root function, and these two blue vertical lines. Okay, so let's highlight the area. So part of it is in here, but there's another part of it which is lying just between those two curves. So you can see that's why it says total area, because what we're going to have to do is find the area of each of these two little regions, and then we'll have to add them up. So the way we might approach this is we could say this one here, let's call that area 1, and this one here, let's call that area 2. So we'll do two separate calculations to get those, and then at the end of the problem we'll say area is equal to area 1 plus area 2. I'll just make sure everything's labeled on here. So the black curve that we're seeing here is just our familiar parabola, y equal x squared. I think everything else is labeled well. So let's focus on area 1. Okay, vertical slices will work fine here. We will be integrating y top minus y bottom. So that'll be root x minus x squared times dx over the x values 0 to 1. Okay, so let's go ahead and do that calculation. Integrating x to the 1/2, you get x to the 3/2 times 2/3, and then minus x cubed over 3, and we're going to evaluate that at 1 and then at 0. So plugging in 1, you would have 2/3 minus 1/3, and then plugging in 0, you would have 0. Okay, so area 1 comes out to 1/3. I might do area 2 over here just so that we're able to see the picture while we set up area 2. And again, vertical slices will work fine there. So we're going to say area 2 is the integral of whatever the area of a vertical slice is. So you want to go y top minus y bottom. You can imagine just putting a vertical slice in there. So y top minus y bottom would look like x squared minus root x. And what x values are we using for this area here? It would be from 1 to 2. All right, so let's go ahead with our integration then. So it look like x cubed over 3 minus, let's think of this root x as x to the 1/2. So x to the 3/2 times 2/3, and we'll evaluate at 2 and then at 1. Okay, so let's try plugging in 2. We'd have 8/3 minus, okay, this is going to be a bit of a messy number, 2/3 times 2 to the 3/2. 2 to the 3/2 is not a particularly nice number, so I'm just going to keep that like that for now. And then we still need to subtract off the value at 1. So at 1, we'd have 1/3 minus 2/3. So if you just look at 8/3 minus 1/3 plus 2/3, that portion there works out to 3. So you'd have 3 minus this messy 2/3 times 2 to the 3/2. Okay, well, one thing you might want to do to this is you might want to say, okay, well, we're just multiplying some powers of 2 together, right? This is 2 to the 1 times 2 to the 3/2. And when we do that, the powers are going to add. So you might just want to call that 2 to the 5/2 over 3. I just think it's a little easier to write down. Okay, final answer coming up. Our total area is going to be area 1 plus area 2. So area 1 was 1/3. area 2, 3 minus 1/3 times 2 to the 5 halves, if you want to write it like that. And then you can just clean up the first two terms and say that's going to be 10/3. So it's like 10/3 minus 2 to the 5 halves over 3. Or what some people might do is just factor out that 1/3 and say 1/3 times 10 minus 2 to the 5 halves or something like that. It doesn't really matter how you give your final answer. The point is just to get the correct value for your final answer. So we have practiced vertical slices and horizontal slices, two different methods for calculating the area between two curves. Thanks for watching.